the link is still the one on e-learning. You can also go ahead and log in on the e-learning because we'll be accessing some things from there. So I will just start with a very quick recap of what we did on Monday, and then we do today's class, which is actually on over versus under fitting of data. So if you remember quite well, I hope you don't have any audio or video issues. So I'm just posting on the chat, class has started. Fine. So now, last time we talked about, let me see. And went ahead and discussed a number of key things. So may I just recap? So regression, which we looked at, is linear regression. And the aim of linear regression is to try to find a line of best fit. That's why it's called linear. That best describes a data set. So if you can remember, we did something like this. So the aim was to learn the best M, which is the slope of the line or the gradient, and the best y-intercept, which we called C, okay? And how does it learn the best or the optimum M and C is by making use of its error function and actually minimizing the error function. Minimization requires some calculus knowledge and optimization techniques. So we had something like this. This is the error function. We are using the mean squared error, MSE, whereby you just take the target minus the predicted, you square the errors, you take the sum, you get the average. And we discuss gradient descent and how gradient descent is able to update M and C in every iteration. So all this you can revise. Another thing we mentioned last time is the partial derivatives, where you have more than two or more variables in a function. You can only do partial derivatives. We saw actually how to do this. Apart from that, we coded all this on Google Colab, and we actually shared the notebook. So we're also going to build up on that notebook. So actually, you should also have a tab for Google Colabs opened, and then it'll be good to go. So any challenges on Google Colabs notebooks? Were you able to open? And do you have any question before I start? So I hope everyone was able to open the notebook that we shared. It's actually there on the e-learning. So let me also open my e-learning on my side here. Okay, fine. So the notebook was actually here, so you can be able to download it. Yeah, about the code, this code, you will capture it. There is a video here. You can go back and watch on Monday's lecture. There's a video here. So that video, we went through the code step by step. You can actually follow by watching this video after this lecture. It's actually very easy. So after watching the video, you follow to be able to get what we were trying to do. through you is also here. I will upload the rest. So all videos, you'll find them up here. All tasks will be up here. I'm avoiding to congest this part. Changes will always be there. You can always be on the lookout. Okay, fine. So now we can proceed to today's class. The notes for today's class, the ones that I'm using, are right here, lecture 2.2a. We are continuing now. So we jumped to linear regression, then we are now back here. Then we will jump there again, back here. Then next week we will jump here. Okay, back here. We are finished with jumping to and fro. We will be landing here. Okay, in deep networks and deep learning, not far from today, because we won't take much time here. We already introduced in introduction to AI. So today is the other term. So if you remember computational learning theory, it's actually here, the agenda. We discuss a lot of things, the theory behind machine learning. We have already discussed performance measures. We talked about gradient descent last on Monday. Linear separation problem, I will talk about it, but today I'm talking about an underfitting. Okay, then I will go to other things. We'll talk about hyperparameters, estimators, the case of dimensionality, and then finally we'll just see how to develop a machine learning algorithm. Good, so today over and underfitting, and then we'll be back to our notebooks to update our code. So just tell the guys when the is already on, and the link is, will always be used this link here. So now, I can now continue over and underfitting, and this is today's topic. So as I go into over and underfitting, you should strive to do code operating. So you should just try and track every question is written like this. The predicted, which is y hat. Okay, so y hat is the one that is equal to m. Okay, m x. So m is multiplied by x, then it is added to c. Okay. There is the target and the predicted. Another word of not a scalar. It's not one value, but it is actually a vector. Okay, so if you look at the training data set, we had the Nairobi office simulated data for price. Price was being determined on the size in square feet. So this was the size in square feet. You have 100 values, okay? You have a vector of 100 values. Okay, that was forming our Y. And then our X was actually also a vector, okay, which is now, no, Y was the price, then X is the size. Okay, the size determines the price. Okay, so X was also a vector. So these are 100 values. All the 100 values in that .cs3 vectors for Y. So in every iteration, you are one value for Y hat. Okay, Y hat. So one value is predicted, and then you compute the error. Okay, I will. This is important because I will come back to the variance of gradient descent. Okay, There's what we call the batch gradient descent, there's stochastic gradient descent, there's mini batch gradient descent, and they are all derived from what we are about to, I'm talking about here. Then the stochastic gradient descent, which is the most famous, has its own variance, which we will be calling TensorFlow. So now let me explain one iteration. So when we start the very first iteration, what is the value for? What did we say m was when we are starting? Iteration 1. The value for m. Someone can call in and shout.
0.
Yes, good. M was 0 initial value, and the same for C. Okay, so this is where we started. M and C is 0. It means that when you are starting the iteration, how will the curve look like? So let me draw that in different color. This is actually important to understand. I love to follow the logic. I must understand what each and every piece of line in any code does. So this is my problem. I like to understand everything in the code. So actually, I normally code from a logical path rather than from line by line. Every line must make sense for me, and I find it to be helpful. So when we start, this started all over, of course, is just an example. Okay, fine. So how does this line look like? So M, when you start, M is as okay. So let me see if my machine has cooled down today. And when we also start, C is also 0. Okay, so how will the line look like when we start? So 0 multiplied by anything is nothing, plus 0. So this will just be the line y is equal, which is actually the line that you actually know is the x-axis. Okay, x-axis is usually the line y is equal to come up with an animation. Your line will start here, then it will start rising, 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 rising. In every iteration, like the notes that I made and shared, iteration M is increasing and C is increasing. Okay, as you go towards the line of best fit. In our example, the one that we had. So now, so here is the thing that happens when you start. That's where you start. So because when you start, when you plug this and this here, the first predicted value of y, okay, the first y hat will be equal to 0. This is iteration 1. Then when it's equal to 0, what happens now? To compute the error, we are going to take, you remember the error is computed by saying y, the target, minus y hat, okay, minus y hat. And then we are going to square, okay, to avoid the negatives. And then we are going to take the summation, and then you are going to divide by n over n. This is actually easy to understand and follow. So what happens if I was to draw every value of y, okay, y1 the first value, y2 the second value, all the way down to y100. We had 100 values, y100, okay. So what will happen is that we will take y1, this is iteration 1 minus 0, okay, minus 0, y2 minus 0, y3 minus 0. So the value of y0, so different from what we were calculating when we were practicing mean squared error. Iteration, the value for y hat remains constant. So we'll minus 0 in every value of y. That's why we wrote this equation. You see x is big here. Okay, so that is how this thing is actually going to be done. And then you minus all of them, minus 0. When you go to the next iteration, the predicted value for y hat is what you minus with every value of, and the cycle goes on and on and on. So in what y, okay, you will minus like 100 times, and then you get the average. That's going to be a problem if we have a large data set. That's where all the other variants are coming in. But today, and underfitting, so forget that one for now. We will talk about that one from. So over versus underfitting is what I want to discuss today. Now, the aim of linear regression is to come up with a line of best fit, the line that best fits the data. So now from today, the word fit and the word train are actually used in turn. So mostly in machine learning, you will hear of fitting the data set. So fit just means loose term for training. Okay, so when I tell you fit your data, I'm just saying just run the iteration to train the data. So the line of best fit, which is the line that best fits this data set. Okay, so if we had a data set like this one, which is the best line of fit? It means we have other lines, but which one is the best? Okay, that is going to lead to today's class. So now, what I've just done by human estimation, this is most like a line of best fit. Okay, will not be it, but it's closer to it. Okay, so most likely line of best fit. In other words, the line of best fit is more generalized. Okay, it kind of explains the data in a general sense. So as I explained, line of best fit, it's the best possible line that is closest to all the points. Okay, so it's like all the points combined. The line of best fit is the one that is closest to all the points, like you see here. So this is actually what we after running our this is the line of best fit, like this one that we came up with. Now, if we had a case of underfitting, the line of best fit will look like this. Okay, so what is underfitting is what we are going to discuss. But before we discuss underfitting, we want to try and simulate underfitting. So go back to, let's open Google Colabs and open that notebook that we had. Wait, yeah. So everyone, we want to open that notebook that I shared with you. Just open the notebook. We want to run something. So mine is actually just here. Okay. Fine. So our notebook was looking like this. Okay. And this was the line of best fit that came. And we were monitoring also the error. I added some lines of code. I fixed the append issue and did a number of things, did step by step. You can watch last week's, on Monday's lecture. Fine, so here, this was the results after running 100 iterations. So we just want to underfit by just running, let's say, run 3 iterations. Okay, so I've changed that line. 3 epochs. Okay, so let's see. Okay, I have to So I lost my data set. I'll just take it from have it. Though sometimes so just try rerunning line by line. There's a data set. It was actually here. Okay, so download and get it. Okay, fine. Cut it, paste it, extract it. Okay, fine. So I think this was our data set. Yes. Just run on the same. So okay, just a moment. Maybe it was done automatically. So let me see my data frame. Okay, fine. Okay. So good. And so run that one. Run that one. That's there. Nothing changes there. That function was fine. Nothing changed. This is only 3 items. So please go through those steps. Iterations. Best fit is actually not the line of best fit. It is something else. So you see, it's not well fitting the data. So this is an example of thing. Okay, so this is an underfitted example. You can actually even see the way the error looks like. Okay, it's fine. So any question on good. So we have actually not discussed underfitting. It's ran this one ahead. So I'll be back here. Okay, so back to the notes. Good. So underfitting will have a line that is not the line of our best fit. And the best way to underfitting is to say the model has not learned enough. Okay, so it is unreliable. Way to this example, most likely the model has not learned enough. Now, if underfitting is a case where the model has not learned enough, so what is overfitting? Overfitting is where the model is too much. Okay, the model has learned too much, that it is so specific, it is too specific to the training data that if you give it another problem that was never captured in the training data, we call it unseen. It was never seen during the training process. The model will not perform well. But if you give it the data set that it trained on, you can even get close to 100%, okay, or zero error because of overfitting. Okay, so the model has learned too much. Underfitting, the model has not learned enough. Okay, so these two kind of things are problems. What kind of problems? So the key thing here is something called generalization. So what is generalization? It's the ability of a model to perform well on previously unseen data. So recall, and I will encourage you to actually get this because it is very important. It will help you a lot in machine learning. So actually there is a, okay, so by now we already know there is a training process. You train or you fit your data. Okay, this is a training. Okay, fine. So I don't know, maybe my machine also today. So there is a train process, train. And then apart from training, after you have trained, then you have to test. Okay. So if way back. So if I have, what did percentage do we train on? What did we actually, if I have a data set, I need to train and also to test. Is like the standard that we normally use for training. Yeah, 80 to 20, 80% of the data set to train. So if you never, you can write actually better than me. 80% for train and 20 for test. Now from Monday, discuss hyperparameters, or next week, we will actually see we subdivide this 20%, okay, into for testing. So we can actually just continue and say here. Okay, we can say here. Good. So use 10% for hyperparameters setting. What are hyperparameters to be answered? And use the other 10. And actually, we will be doing this. We'll be dividing our data using this. Okay. So actually, what we should have done for the 100 that we had, we could have used 80 rows to train. Then the last 20 rows, we use them for testing so that we actually check, say, why. So 10 hyperparameters setting or meta parameters, hyperparameters. These are actually important. Hyperparams. So I will come back here. So let me just write it. And the rest now we use them for testing. Good. So this is like the standard that I normally use to divide your data set that you have. So now, then there is something that now called cross-validation, which I will also talk about, that you can actually, okay, I will mention what cross-validation is as we go by. So fine, what is generalization there? Well, on the data set that you did not see during training. Okay, so if you train or you fit your model on the to perform this, but actually you're not doing well. Okay, so there are two types of errors that we are going to introduce that you actually have to also. So generalization is measured using the test error, or what we call the generalization error. Okay, that is calculated on the test set. But before that, there is an error that we know during training, like what I was demonstrating up there. Okay, those errors that we are calculating in every iteration during training, they are called the error. So there are two types of errors: the generalization error, okay, and there is the train error. So during training, which we have actually gone through an example, remember we were using regression as an example to understand computational learning theory terms, rather than just learning theory, but actually to see. So I am reminding you here, recall that our main aim was to minimize the train error. During training, we were trying to minimize the train error. Okay, this error that we compute in every iteration during training is called the train error. So we were trying to minimize that error using gradient descent, calculus, optimization, trying to find the minimum. Okay, now we introduce another goal for machine learning. That other goal is the goal of minimizing the test error. Okay, so after I have trained, like done, and we have gotten the line of best fit, now we start to test. During testing, we also want our test error to be minimum. So the question is, how do we actually go through that? Minimum that you have already seen? No, but on the data that you have not seen on the test data. Okay, fine. So for example, after training on the 100, okay, on the 100 in the Nairobi simulated data for office prices, after training on the 100 rows that we had, we gave it a small task. We asked that if the size of the office is 100 square feet, okay, or foot, what will be the predicted price? Okay, and it told us something 140K or something like that. So the question is, how accurate is that? Okay, that 140K. If it's actually logical and accurate, then our model has generalized well. If it tells us the price of 100 square foot is 1 shilling, then we know we have a serious problem there because it's not logical. Good, fine. So how do we go about minimizing the test error? So here's the thing from statistics. Both the train and the test errors, they come from the same probability distribution. They're actually relatives. That's what I call them here. So these guys are actually relative. So the assumption we are going to make here is that train and test error, they are identical. What does that mean? So if I am minimizing the train error during training, so consequently, because they are drawn from the same probability distribution, I'm working still on the same distribution. I'm doing my estimates. So as I reduce the train error, I am also reducing the test error. So what does this mean? If I find my model is not doing well during testing, actually what we normally do is just train with more data. Okay, so just do some more training, okay, to make your model to be more and more better. Just do some more training. Maybe you have done less training. So we call things which come from the same probability distribution identical. The next assumption that we make here is that, so that slide is not complete due to the Microsoft whiteboard. So there are two assumptions drawn from statistics. Good, same probability distribution. And okay, so, okay, I thought there was something missing here. Then the next is that each example is independent of each other. What do we mean? So each example is independent. So where's my data? Yeah, it's better to explain it using this one. Fine. So each example is, so I can zoom in here. So each example is independent. So this is independent from that, is independent from that, is actually going to be important. So what does that mean? So we normally call these things, this series of events that are statistically described as IID, okay? And so this talks of independent and the way the distribution is, as opposed to IDD, okay? So without this can be best described when we were doing samples with replacement and without replacement. So when you're saying with replacement, you're picking balls from a bag and you're dependent on the pass event, okay, because you're kind of returning things in the basket. So the probabilities are not kind of changing, okay. So, but when they're, no, that is independent. But when you're picking without replacement, okay, then the story kind of changes. But you don't actually have to cram all this, but you just have to know that the series of events, for us to make the above assumptions, these ones must hold, okay? So statistics dependence of every event, whether they are dependent or independent, okay, and whether they are identical or not, okay. So the way we describe are different distributions. So I will actually return to this when we are doing Bayesian machine learning, because we will see some distributions are actually IDD and others are IID, like the multinomial distributions, and I will cross the bridge when I get with you guys there. Fine. So the train and the test error, they are related. So we have no problem. So back to under and overfitting. So what do we want? Given the mentioned realities, the performance of a model is measured by, number one, the ability of a small, okay, that's the first thing we want, the small training error. It must reduce in every training iteration. Number two, make the gap between the training and the test error to be so small, okay? Error. Number two, during testing, we want to minimize the test measures of the performance of any given training. So to monitor the error. Is the error reducing in every iteration here? And we have the error. So when we started this iteration, the error was, which number is this? The error was somewhere 500K. And we were able to reduce the error about is improving. So we say that that model is doing well. So those are the two things that we aim at. Now that's where under and overfitting comes in. So the official way to define underfitting occurs when the model is not able to obtain a sufficiently low error value on the training set. Okay, so if you are not able to attain or to minimize well the training error, you will run into you saw the other one was almost touching the two axes. Okay, so the closer it is to the two axes, the better the minimization. So okay, fine. So underfitting is whereby you have not trained enough. So that means that your training error is large. Okay, it has not been minimized well on the training set. Overfitting, when the gap between the train and the test error is too large. Okay, that is overfitting. Fine. So now the thing that you should actually have in mind is how to handle such a problem, over and underfitting. So before I discuss that, I want to discuss something called the model capacity. Okay, and assuming, so let me see if I put something here. Yes, let's assume our data looks like something like this without the line. Just imagine the line was not there and we have points going like this. Okay, so the question is, can I be able to draw a line of best fit? Which line best fits this data set? Actually, there is no way I can have a line of best fit. Okay, but here I can have a line of best. It's easy because the data is kind of increasing. So here there is no way I can have a line of best fit. This data set is actually drawn from the Gaussian distribution. Like I mentioned last time, linear regression will work well if the data that I have is from a Gaussian distribution. But I won't go into that today. But this data set actually came from a different distribution. So the line of best fit won't work here. And we actually have a problem. So if I want to draw the line of best fit, no matter how much I try, when the data looks like this, it can't work. Okay, so it can't work. What does it mean? I will always be underfitting. Whatever line I place here, I will always be underfitting. So what is the best way to start solving this problem of underfitting? Of functions, okay, or a model that is able to do more. And here is where we will have the difference. There are things that linear regression cannot do because of its capacity. There are things that K and N cannot do because of its capacity. There are things that neural nets can do because of their capacity in deep learning. So the difference between every algorithm is simply the capacity. So can we increase capacity? The problem is that, so before I even go to the nodes, the problem is that the more I increase capacity, the more the problems I can solve very complex problems. I can drive cars using machines. I can do crazy predictions. So those models are models of high capacity. The problem is the more I increase capacity, the more I run into overfitting. And the more I decrease capacity, the more I go into underfitting. Okay. So we need a balance, and that balance is going to be achieved using the principle of Occam's razor, which you actually have the dots here together, even into a lot, is that we're just trying to strike a balance between underfitting, which is not doing well, and overfitting, which is actually not even good. So what balance do we actually strike? So before we answer that, we discuss capacity. It is one way of controlling over and underfitting, but I find it more a way of controlling underfitting. Okay. First of all, how can we improve on underfitting in a linear model or in regression? So for example, if my data set, like I've said, you refer to this slide, looks like this without the line, there is no line of best fit here. That is because of the capacity of a linear regression. So you need a different type of regression to fit that one. So why is linear regression called linear regression? Because it fits a line. Okay, you see, things are jumping here. You see, linear regression fits a line, but this is not linear regression. Okay, so this is a line which is linear. What is this? So if this is linear, what do you think we call this one? My calculus friends. It's actually just polynomial. So from linear, which other polynomial is next? What do we call polynomials of order 2? Yes, Isaac.
Quadratic.
Yes, it's actually quadratic. Thank you. When we go to order 3, it's cubic, and so on and so forth. So in short, we need a higher order polynomial in order to fit this data set well. And that is capacity. Okay. So that answer is achieved by increasing capacity from linear to quadratic. Good. So the solution here, example, is to increase capacity of regression to allow high order degree polynomials. The moment you allow high order degree polynomials, you run into an action called polynomial regression. So you remember from last week, not last week, I keep saying last week, it's on Monday, where those notes, let me see, no, this is today. So on Monday, we start by saying we have these types of regression: linear, logistic, polynomial. So you see where polynomial regression is. It's actually here. It's a polynomial regression. So polynomial is just allowing high order degree polynomials apart from linear. Good. So today we have just mentioned polynomial regression. Higher model capacity can solve more complex tasks, but it suffers overfitting. Lower model capacity is limited, and it's also prone to underfitting, okay, to underfit the train data. Fine, so we have examples here. Example 1, linear underfits. So this is the example of how linear underfits this problem. Quadratic fits what, but if I use a degree 9 polynomial, it overfits. So notice overfitting solves a problem, but its complexity is way high. Okay, it's overfitting the problem, or better put it, solving the problem. Fine. So we have a principle called Occam's razor. So it just says among its competing hypotheses, choose the simplest. Okay, the simplest possible. So what is simplest for us in machine learning? It's the function that is more likely to generalize well. However, I wrote this one after going through, we must still choose a sufficiently complex hypothesis. So it's a balance. It's not easy to achieve low training error. So how do we track this one? The easiest way is to track the two errors. The first error is the train error, computed in every iteration during training. The second error is the test that is computed after you're done training and you're testing. Okay, so here there is a plot of the two errors. The first one is actually so first you have the training error that is actually reducing in every iteration, you can see. So it is kind of reducing as the capacity increases. Okay, so it is asymptotic maybe to this one. Okay, so in the epoch, the train error always reduces. But as the train error is reducing, every generalization error is a test error. Okay, so the test error will always be above the train error. Okay, but the problem is that the more you train, the more you're running the iteration, you're increasing the train error. But I am increasing the. Yes, the more I train, the more I overfit. That's the thing that we're just saying here. So that's why we call this underfitting zone. And this other one is called the overfitting zone. The balance is called optimal capacity. Okay, so there are various ways to reach this optimal capacity, and it is what is encouraged by Occam's razor, to just try to strike a balance between underfitting and overfitting, and then trying to settle in the middle. So yes, training and training and training is good, but the more you do training and training and training, the more and more you are overfitting. You're increasing capacity, but you are overfitting. And the more you overfit, the more you are moving away from generalizing well. So if you can put all that together, it will help us to do a lot. Now, the official way to handle this problem is called regularization. Okay, so actually regularization is one of the most important things in machine learning. The other number one important thing in machine learning is, of course, optimization. Is the most important, the most studied. Without calculus, there is no machine learning, because we learn by optimization, by finding the minima or sometimes the maxima of a function, and that function is the loss function. So the number one important aspect in machine learning, if someone asks you, is optimization. Why optimization? We learn by minimizing the function. How will I find the minimum? By actually trying to, I have to find the minimum of the curve, and that information is found by finding the derivative of the curve. That's the whole story. Then after optimization, the next number 2 important thing in machine learning is regularization. Okay, that's number 2. So today we are going to discuss regularization. Then we are going to regularize the loss functions that we actually use on Monday. So in regularization, we are going to make a modification. This modification is going to balance the capacity, trying to find an optimal capacity. Okay, and let me switch here. Okay, we are going to try and find the optimal capacity. So let me see. Okay, we went through. Okay, yes, this is what is missing in that slide. So let me just look into it from here. Yes, a modification. This modification is going to reduce the generalization error, but not the training error. So if you just sit for a moment and try to reason this thing scientifically and computationally, and as a simply sophisticated machine learning engineer, you're able to see this thing. So this is the generalization gap here. Okay, if I can reduce this, I hope I could write here, if I can reduce this but maintain this one, okay, what is this one? It is the same as this one. Actually, we want the error to reduce in every occasion, in every epoch, in every iteration. The problem is that while I keep on doing that, I have a problem. There is another error called Mrs. Test error that is actually just misbehaving by rising. So the goal here is actually like we are having a kind of a tussle between the two. Yes, I want this to reduce, but at the same time, I want also this to reduce. So if I can reduce this, I don't know which color is this, but I think this is blue. So, and maintain this one, then that is the golden kind of thing. So here is the thing. I want you to capture this one so that you don't struggle with machine learning. I've met so-called machine learning engineers who can only peep and call a library and they call it a day. That won't help. We need to solve problems, but first we need to understand how this thing actually works. So this one loaded. So if I can be able to, you see what I want, important things. Number one, I need this to maintain, it's reducing, yes. I want my capacity to increase. You know, a higher capacity means I can solve more. So I want this capacity to move somehow. But the problem, remove it, this generalization gap is increasing. And thing is that if we can be able to reduce, if there's a way we can reduce this guy downwards, then we can increase at liberty and we can maintain this one, okay? That one is achieved by Mr. Regularization. Good. So that's why I repeated that slide, that curve. It is actually summarizing a lot, that single curve. Good. So you can understand it in your own way. You can try to check it out. I could have this curve maybe in the CAT or exam and just try to see if you really were able to understand how important regularization actually, extremely important. So from optimization, which is actually making our error reduce in every iteration, regularization is the next important thing that can allow me to increase my capacity and at the same time not increasing the generalization gap, the difference between the test error and the test error is here and the train error. You can write just will later lead us to deep learning and the theory in deep learning. So in our linear regression, like in above there, okay, we all know the equation of a line is C, okay, where M is the gradient and the C is the y-intercept, okay? And those two things are actually important as far as the linear equation is concerned. In fact, the part that is the linear equation is usually just this part. No, that's too far. So let me take this one. Yes, this is mathematically speaking, this is usually the linear part. This other part is called an affine, A-F-F-I-N. Now, why is this important? It's just important. Now, for example, if you play around with linear curves or graphs, you are able to see some important things. So there's usually something that I normally use here. Let me see if I can get it. So that you can actually see. Not so many bookmarks anyway. No, I can't find it now. So I will show it maybe later when we get there. So, but for now, the line for equation is y is equal to mx plus c. Notice that we were calculating y hat using that. Okay, so actually we'll just say y hat is equal to mx plus c. That's how we were calculating y hat. Y hat is the predicted. Fine. So we use gradient descent to learn. Gradient descent is used to learn the optimal or the optimum or the best M and C. Okay, X is given and Y is predicted. Okay, X is usually given. Like I made those notes by hand. You can check on them. Now today we transform. We now transform this to Y hat is equal to W. So W is taking the place of M. And we're going to call W the weight. Remember our neural nets? Now we introduce our weight, okay? There is a weight multiplied by the X vector plus in C, now we are using B. So W is a weight. In our example, it's a scalar. Scalar means one value, but we will get to a place whereby W will be a matrix, okay? A matrix of weights. But for now, W is a single value, it's a scalar. And X is the input vector, and Y is the output vector or the predicted, and B is a bias scalar. Again, bias is a value in this example. So we now have Y hat or Y is equal to WX plus B. Now, the idea in learning is to find, okay, so I rewrote this one, find an optimal weight value. That's what we want to learn when we are running gradient descent. We want to find the W or the M, like what we did here, the optimal W. So the best way to say that is we want to find an optimal weight that makes the value in the output more probable. Okay, so it's just a way to say that's how we train. We all know we do this by minimizing the loss function. We already know that. So now, how are we going to do regularization? We are going to do that. What's happening to my board? It's actually gone crazy. Okay, fine. So maybe I just switch here. Fine. So this is what we are going to do today. In linear regression, there are two types of regularizations, okay, or regularizers. The first one is called L1, and the second one is called L2. And we are going to use both. So what is regularization? We have said it is the official way to avoid over and underfitting. Okay, so both regularizations in regression L1 and L2, they avoid overfitting by penalizing large weights. They are going to this zero, which I'm going to expound further on Monday. Okay, so in other words, they are going to downweight features that are unlikely to generalize well. And I mentioned this when we were introducing AI, but today we actually want to apply it so that we avoid how. So the question is, how do I avoid overfitting here? So if there can be overfitting, though linear regressors are not prone to overfitting at times. So how can we avoid under and overfitting? Number one, increase capacity. Okay, how do I increase capacity? You can allow high order polynomials depending on your data set. Number two, you can do more training. Okay, you can do more training. But remember, the more you do training, the more you're overfitting. Okay, the story just kind of mixes together. So now, regularization is now the official way to avoid over and underfitting in all models. Okay, what we are looking at is regularization for linear regression or for regression. Okay, how do we regularize regressions or regressors? We use L1 and L2. How do we regularize neural nets? We will get there. Okay, how do we regularize KNN? How do we avoid overfitting and underfitting? We'll get there. How do we do it for naive bias? We'll get there. Some models don't have regularized. I will talk about that. So today we talk about regularization in regression. Okay, there's a question there. I think now it will be answered in a moment. Fine, so there are two ways. The first one is called L1 regularization. The second one is called L2, okay? L1 has another name, it's called lasso, and L2 is called ridge. So again, if you may go back to Monday's notes, you see again, we had ridge and lasso here. So by now we will have already talked about linear regression, polynomial regression, ridge, and lasso. I will mention stepwise Monday. Fine, so how does this work? I'm going to revisit the error function. You remember the error, the difference between the predicted and the actual. Okay, it's actually very easy. Predicted versus the actual. And we are going to start with L1. Okay, L1. L1 regularization, which is also called lasso regression. So forget lasso. I am not a statistics guy. I'm a computing person. So lasso is the term they use in statistics. You have to know statistics, but sometimes I'm not a very fan of statistics. I'm just a guy in computing, but I love statistics. But at the same time, I'm not in statistics, whatever that means. So L1 is the name that I like so much. So L1 is a linear function. Okay. What is L1? It's very easy. Like I said when we were revising maths, I said that there are two ways to explain things. You either explain the easy way or you are a mathematician. So in math notations, but those notations are actually, they look complex, but when you start explaining, they're actually very easy things. Okay, so I'm going to explain in an easy way, but also you have to be familiar with the notations. Good. So you already know that anytime I write, I don't know if my board is back or I just reopen another one. Okay, fine, it's back. So I'm going to quickly discuss some things which we didn't revise, but I reserved them to mention them here. Number one, we know that when I write maybe X, my pen isn't doing well. Undo. This one. So anytime I write X like this, okay, so this is just X with the two bars surrounding it. It just means absolute. Okay, so if X is negative 2, it will say X is 2. If X is 2, it will just say it's 2. It's absolute. Okay, so the next thing that we want to explain is so when we are revising matrices linear algebra, I was to mention norms, but I didn't. So if you have a vector and you are asked to get the norm, okay, the norm is just to get the distance, okay, or the magnitude. So if you're writing, you can just say norm is the magnitude or the distance of a vector. Can't write much today again. Magnitude of a vector, okay, is actually its norm. Remember, vector has two things, magnitude and direction. So how do you get a norm is very easy. So because the norm is the magnitude or the distance, is usually, so the norm has different degrees. Okay, like you remember the moments of a curve, the norm has different degrees. There's the first norm, the second norm, the third norm, the p norm, and so on. So easy if, let's say, we have a vector 2, 3, 4, and you're asked to get the second norm. Let's say this vector is called vector x. So the second norm will be written as, this is how norms are written. It will be written as x double bar, like this. Okay, so this is the second norm. Good. And since, yes, so sometimes you bring also the power here. So how do you get the second norm? Is easy. It's just the Euclidean distance. And I hope you remember. So triangles, very fast. Okay, I have M, N, and P. Good. So how do we normally get P very fast from Pythagoras theorem? Anyone can call in. This is high school. I know it's a long time ago. Yes, Anthony.
M squared minus n squared.
M squared minus, no, M squared is right, N squared is right, but how do we connect the two? Anthony has started off. Do we minus or do we add? Let me see, some people raise their hands. Yes, still on Anthony, yes. No, Anthony is gone. Waweru.
Yeah, so it's m squared minus
Yes.
n squared, all of that under square root.
And you find the square root.
Yeah.
Okay. Yes, true. But actually what I should just be asking is how to find m. Okay. It's actually very easy. Yes, I understand now what I was trying to ask versus what Anthony had. So if I'm trying to find m, I will just now say n squared plus p squared, and then I get the square root, right? So I think I'm not... yes, okay, fine. So that is drawn from that one. So the second norm is just, no, I don't have a pen, so by one, I've bought. So 2 squared in the vector now, plus 3 squared. It's very easy. These things are usually easy. Math is the easiest. 4 squared. Then get the square root. You notice that when you do this one, you will get a number, okay, or a scalar. That scalar defines the distance or the magnitude of this vector. So easy, that's the way it is. If you're asked to get the p norm, you will say 2 power, sometimes you can square it, or you can say 2 power p plus 3 power p plus 4 power p divided by the pth root, or whatever that means. So this is the square root because we are using 2. Anyway, that's just a way of saying the norm. How do you get the norm of a matrix? You just square everything, second norm, then you get the square root. There is no complication. So this summation here just means you add everything as you square them. You can see here. That's how we get the norm. But now here we are not going to get the square root. So this is what we are just saying, is that L1 is drawn from the first norm. Okay. So L1 regularization is drawn from the first norm. The first norm is always the same as Manhattan distance. If you remember our distances, when we were doing, what were we doing? When we were doing clustering, there was the Euclidean distance, there's the Manhattan distance. So Manhattan distance is usually like the first norm. What is raised to power 1, so we don't bother writing the powers. So this is what we are going to do. We are going to take the function, the loss function. Remember the loss function is MSE, mean squared error, which was defined like, you already know how MSE looks like. So where is that? Yes, we already know how MSE looks like. It's last week's notes, MSE. You just follow through, you will never get lost. Good. So this is how MSE, mean squared error, looks like. Take y minus y hat, square it, add everything like we were saying, divide by n. Nothing complicated there. But remember, y hat is the same as mx plus c, okay, the predicted, depending with my m and my c. So as my m and c is being updated, I'm getting closer and closer. The error is reducing. Okay, that one we know. So we are going to take this. So regularization is applied to the loss function, to the error function, to the cost function. Those things mean the same. So we are going to take this function as it is, and then we are going to regularize it. Okay, how do we regularize it? This is what L1 does. Takes the function, then we are going to minus, we are going to punish. Okay, we are going to punish the way it is. We are going to minus the first norm, okay, without taking roots. So we are going to take the weights. So this example is simple because we only had one weight. Remember, W has taken the place of M. Okay, like I've done the change there. So we only have one W or one weight. So we are going to take the weight absolute, forget its sign, forget its direction. Okay. And if I had 3 weights, I'm going to add all those weights. Okay. Then I'm going to multiply the weights by a hyperparameter, which is lambda. Okay. And so we are going to take the loss function and then we are going to punish. We are going to subtract lambda multiplied by first norm in L1. L2 is the same, it's easy. You take the loss function as it is. Okay, so again, my board is, I don't know. You take the loss function as it is, then you minus lambda multiplied by second norm. It's not difficult. Second norm means that you just take the weight, so we only have one weight, and you square it. Okay, this is a second norm. Square, you don't have to say absolute because when you square is always absolute W. Okay, so in every iteration, this is what we are going to be minusing. Okay, but now, so back to L1, this is what we are going to do. This is the modification we are going to do in the code, and that's now going to be the first lab assignment. Okay, to regularize linear regression using L1 and L2. I've already written down the question and this in a minute. So I will have this part like we did, and then we want to punish, we want to subtract lambda L1 and norm 1. So forget all those terminologies, just the absolute of W. If you have many W's, you add the W's. So fine, so now, remember this was the loss function. To train the model calculus, we have to get the minimum. We have to minimize the function. And how did we do this? We got the derivative. Okay. So after writing this, after modifying, remember regularization makes modification. After modifying the loss function, this is now what we are going to optimize. This is the new function, the regularized function that needs to be now optimized. So after I have written this thing down, I'm going now to compute its derivative. Okay, first order, partial derivative. Okay, you already know from what we have up there, the derivative of this part. So the question is, what is the derivative of this part? That's an assignment. And then that is what now we are going to use in every iteration. Anyway, I won't explain much because I want you to engage in assignment 2. Now, this hyperparameter, we are going to set hyperparameters from next week, has to be greater than, if lambda is too high, than 0, it will be the first thing, because as I go to the next section, if lambda is closer to 0, you will be tending towards overfitting. Okay, so lambda is a parameter that controls. So as of now, I'll just give you the value of lambda. Okay, then the rest will just stand as they are. So fine. So L2 versus L1, okay, is something that I will discuss, I think, from Monday. But now L2 regularization is easier to optimize because the derivative is simple. L1 regularization derivative is slightly complex, not more complex, slightly. L2 prefers many small weights, but L1, it prefers larger weights with a lot of weights set to 0. This is what L1 is going to do. It's going to set some weights to 0. And because weights are associated with, so why do we have one weight in our example? Because we have only one x, which is the size. Okay, so if I set this weight of this feature to 0, it means I'm ignoring that feature. That will lead us to Monday, where we will be discussing feature selection. Okay, so L1 has the power to do feature selection by setting some weights to 0. L2 can't do feature selection, okay, but it will set some weights. Some weights will be so small, closer to 0. Okay, it will have so many smaller weights. So what we will be doing is that you can give L1, Mr. L1 and Mrs. L2, you can give them a weights matrix with the start weights, like we had for, we'll be doing this in deep learning. You can give it some 8, 19, 20, 1, and then 9. And then they will transform this matrix into something else. If I give it to L2, it will transform it into very small values. If I give it to L1, it will make the values to be 0, and others will be large. They might grow. But for now, we reserve that one for next week. How we play with lambda is important. Excessive lambda, underfitting. When the lambda is approaching 0, you are overfitting. Medium lambda is what we'll be talking about from Monday. That leads us to feature selection, which will be the next one. So today, we want to regularize linear regression using L1 and L2 by making modifications to this our code. What are you supposed to modify? It's the assignment. I won't tell you which line to modify, what to update, or whatever to do. But whatever line you will modify, you are going to comment on that line. Okay, so is there a question on L1 and L2 before I now do the assignment? Yes, George, your mic is on. Okay, so anyone with a question? So we are good. Fine. So someone call in, discuss regularization and why it's important in the fewest words possible. Basically, just understood. And from the notes you are taking, by the way, there's a lot to note down. Yes, maybe we can start with someone will be telling us something as we go on before I discuss the project. We can start with Rebecca. Rebecca, are you there? Yes, Rebecca, how are you?
optimization.
You can get closer to the mic.
Can you hear me better now?
Yeah, fairly.
Okay, so what I've understood by regularization,
Yes.
basically when you have a model and you are just basically trying to overfit, where you're trying to make the model work in a data set that it hasn't encountered before. I understood that overfitting is basically when the model works very well on data that it has encountered before, but when it comes to new data, it doesn't work so well. And underfitting is when it doesn't work well in both the training data set and the actual data set. And what I understood, avoiding regularization using 80% of the training data to train the set, and then 20 to test it basically. Yeah, I think it's and it helps to choose the preferred model complexity, so that the model is basically better at predicting even data it has seen before.
Yeah.
That's what I've
Very, very good. Actually, you have gotten a lot from one class. Yes, that's true. Rebecca is right. Yes, so we actually use regularization to choose the best model capacity. And yeah, you have heard what she has said. Actually, that is the perfect flow. Now, the lecturer said that optimization is the most important thing in modern day machine learning, followed by regularization. Why do you think he made that statement? Anyone to weigh in on that? First, most important thing in modern day machine learning, optimization. Next, regularization. Why do you think he made that statement? Anyone can go in just briefly. We can have Edmond talking to us. Edmond, are you present? Guys actually have their hands up. So maybe Edmond, I'll be back to you. Yes, Joseph. Yes, Joseph.
Yes, I think we look at optimization first because
You can be closer to your mic a bit.
Okay. Can you hear me now?
Yes.
Okay. We look at optimization first because we need to find the optimal capacity before we can think about using regulation to increase this capacity.
Okay, yeah.
Increase.
Yes.
I think because in machine learning, what you are trying to reduce the two errors of the error for the training set. That's I think the reason why the first priority is a optimization error is because when you optimize, you also improve in the generalization.
Yeah, very good. But now optimization will improve now. The test. I will summarize. Good, but after Gabriel. Gabriel has an addition too. This is good.
Yeah, I think the reason optimization is important is because of data sets that exist in machine learning. Even
Yes.
if you create a model that is good at generalizing the data, but
Yes.
you can't, it takes insane amounts of computational time. It would
Yes.
not be ideal.
Mm-hmm. Okay, fine. Good, great contributions actually there. And I will now use all the statements to maybe make just like one statement, which you can actually write down. These are the terms to use when you attend that machine learning conference, or just when you're coding your model, you code like someone who actually understands what we are actually building, rather than just getting a code from GitHub and then updating our CVs as machine learning engineers. It doesn't actually do much. Yes, training error. That's the first thing. Okay. Optimization helps us to reduce the training error. Remember, that was the first goal for any model. Okay. Then number two, regularization now helps us to reduce the test error. Okay, in a summary, Joseph, your hand is up. You have an addition, or it's the previous? It's the previous hand. Good. So, guys, those two statements, I find them to be important. Optimization helps me to reduce my train error. Regularization helps me to reduce my test error. Those two statements are going to help us a lot. So actually, you have to know how to do optimization. Optimization means we are getting the minima of the error function. Sometimes you can do regression. Very quickly, I go back to the notes. I don't want you to overfit. You know, studying for exams is overfitting. You will do well in the exam, but you won't do well in real life, most likely. So I don't want you to overfit for exams. I want you to generalize well, even for real life. Now that you guys are going out there in after a semester, most of you are already out there, have received the reports, and your supervisors are saying, yes, I want to continue working with this one. I've never seen a student like this. He learns so fast. I have made visits before the virus pandemic, and I was getting a positive feedback, like always. So now, when we step out there, if we did overfitting, we won't be doing well. But if we generalized well, we'll actually be good. Now, take for example, let me say back to these notes, back to the introduction notes. We are doing linear regression, and we're using the mean squared error. If you remember your loss function, no, this is for today. Where is that? 2.1. Good. I just demonstrate something here. You see, the error function you're using is important. Remember the loss functions? We have a number of loss functions. Okay. See, mean absolute error. Hubbard loss function, or even better, uses that use one, log hyperbolic cosine, as the error function. How do you go about that? To number one, optimization. To optimize, okay, to optimize, you need to get the minima of this function. To get the minima of this function, you need to get its derivative. To derive this function, you need to know how to calculate derivatives of logarithms and hyperbolic cosine. of which I summarized when we were revising. And you can actually calculate the derivative of this one. Use this one as your loss function, and then come up with a paper and say, when I use log cosine hyperbolic is better than when I use mean squared error, than when I use mean absolute error. And you can compare the error functions and so on. And there are many other error functions. For me, any function with this shape is a candidate of an error function. You see those shapes that I was thinking about. An inverted parabola or something like that. You see the shapes they share. So fine. So don't overfit for exams. General for real life. So very quickly, good. So today's lecture will be available. The recording, I think this one I'll upload immediately. So quickly, back to e-learning. So this is the task. You see the task here? This is the task. And the task is so easy that the deadline is midnight. This one you can even do in the next 1 hour and you're done. Now the thing is that we are doing in groups. Okay, maximum 4 guys. Just read through this. So before I release you, I want to give you 3 minutes. Please read through this. And if you have any question, you ask me. I'm just going to take a glass of water in the kitchen, then I'll be back. So please just go through this one, read this, and if you have any question, I'll be back in exactly 3 minutes. And then from there now, I will leave you to now continue with the coding. I already did the first part here. You already have this notebook. You've seen how we open it. And you are going to write all your code on Google Colabs. They are going notebooks, and there's some instruction there. So read through, and then to be finished. Okay, fine. I'm back. Okay, if you have questions now, I think I see questions. Okay, guys are talking of the deadline. Why? This is just something so small. The deadline is 12 midnight. I don't see that to be tricky. So maybe someone can call in. Maybe there is a reason. Is there any logical reason why we should push the deadline? Jaden, why? Yes, yes. Hello. Yes, we can get you. You want to code overnight? Yes. Mm. Yeah, I'm going to upload the video. Guys can follow through. It is actually something small. Is only that you will have to go through and recap. Okay, fine. That is Jaden's reason. Anyone else who feels stuck on the deadline? We're actually going to be coding fast. Isaac, what's up?
Oh, hi.
Hi.
Okay. For me, the reason why I'd want the deadline to be extended is because we're not
Yes.
working same place. So like we're meeting like probably via an online platform, and that like constitutes to a lot of issues. So we don't know what will happen between now and midnight. So by extending
Yes.
the deadline, it will make it reliable such that if there's any issue, at least overnight or before now tomorrow
Yes.
morning, as Jaden has said, guys can actually get away to actually have the work completed.
Okay, fine. Okay, fine. Yes, I understand. Kenya Power is sometimes messing up, and there are rains. Some poles may have collapsed, and many things are happening. Now, yes, that's true. So now let's do this. You see, the deadline says that you just ensure by before 12 midnight, you have sent me the link to the GitHub. It doesn't mean the GitHub should have the code yet. The Git link to the account of the group leader or whoever will send the link. But I will expect everyone to just have the code in your GitHub. Then you'll just send one link of the group leader. So ensure the link you send it before today, but ensure the code is up there before Monday, the next class. Okay, I think that's now fine. So ensure you have coded by Monday next class, but ensure the link is there. So for now, so please ensure you send the link of the leader before the day ends. Yeah, so if you send the link late, it doesn't mean that the link should have the code, but if you send the link late, it will be counted as late. Yes, Waweru.
There are some parts that mention that we need to have
Yes,
show working. Yeah, either on
like in the assignment. Okay.
Yeah. So do you expect us to do that? Like to
Yeah. You see in GitHub, you can upload code plus more. In fact, this is the beauty. Now, thank you. You see, why is this called Google Notebooks? Many of you already know. Apart from code, I can also do text. For example, I can explain this line using text. just press there. I can show my working here, okay, or something like that. So you can do them inside the code, or you can upload something, a separate file explaining that part of code. I'll actually be marking the working on these parts that I've actually talked about. So it's here, let me see. Yes, there's some working to be done, especially on revising on the derivative and checking them out. Also here, just follow these instructions. So these ones, you can either do them alongside the code, or you can actually upload maybe a .pdf or docs or something like that. Yes, the working actually has to be short. That's why we are doing it and you understand something. Yes. Any other? Let me see the chat room.
To fill in our
Yeah.
groups
Yes.
does not have edit access.
You can be able to edit.
Yeah.
Okay. I'll fix that just immediately after this. Okay, that's easy and fixable. Any other? So now we are good to do the assignment. When we meet on Monday, we are going to discuss feature selection, which is a build up from L1. Okay, feature selection. I might tie it with dimensional because they're related, but I will see how it's going to be. So if there being no any other questions, I think for today we can actually be able to end it there. You can just say hi to me there, and then I will be good to go. And,